I can first introduce the Professor Jiang Shaofeng. And Shaofeng is an assistant professor at the Center on Frontiers of Computing Studies, Peking University. He obtained his PhD from the University of Hong Kong in 2017. He was a postdoc researcher at Weizmann Institute of Science and an assistant professor at Aalto universities. His research interest is theoretical computer science, with a focus on algorithms for massive data sets and the foundations of data science. Okay, now let's welcome Shaofeng for his talk.
Okay, thank you so much for the introduction, Jialing, and I'm very glad to speak here at this workshop. So today I'm going to talk about recent work about online facility location, which is a fundamental online problem, and with predictions, which is a new setting. And this is a joint work with Zhi Liu, Yu Lu, Zhihao Chao, and Yubo Zhang. So okay, so let's first talk about the motivation. So algorithm design with predictions, this is a new direction, and the motivation here is that in traditional algorithm design, people mostly focus on the worst case. So while this is a very strong guarantee, but often this is too pessimistic to be useful in practice. On the other hand, with the emerging ML techniques, for instance, RL and so on, one can build some very strong data-driven algorithm that can leverage the structure of the data and usually perform very well in practice. So the gap here is to design algorithm with a learned predictor. So assuming we have some learned predictor to the algorithm, and then we want to have some better performance and ideally go beyond the worst case analysis. Right, so that's the motivation. And okay, so a natural question to ask here is, so since we have the predictor, can we simply trust it and use that to simply guide us to do the decisions? This is sort of complicated. The reason is that the state-of-the-art sort of predictors or classifiers usually suffer some problem. For instance, the very small but structural noise can change the classification result of a deep neural network significantly. Unfortunately, such kind of not robustness is not easy to bypass, and perfectly robust ML predictor is unlikely to exist. So when we design such kind of algorithm with predictors, we have to consider the untrusted predictor. To this end, we introduced this so-called LV framework proposed by Likoris and Vasilevsky to utilize the untrusted predictions. Formally, they assume that, so as we said, they assume that we have access, the algorithm has access to an untrusted predictor, and we model its error as eta. So it's important to note that this eta is not known to the algorithm in advance. So the algorithm is blind to whether this predictor performs well or not. And the goal here is to design an algorithm that is both consistent and robust. So what do I mean? So by consistency, I mean, if this error eta is very small, means that the predictor is very good of quality, then our algorithm should also perform nearly optimal. And here, actually, this requirement may even bypass certain theoretical lower bounds. And this is exactly the part where we do beyond worst case analysis. And recall that our motivation here is to think about the robustness. So the robustness here really means the when the eta can go to infinity, which is very bad, then we still want our algorithm to perform has a reasonable performance in the worst case sense. So that's the overall framework. And such kind of framework is actually so this kind of algorithm has already been considered before, just that the framework was not sort of formalized. A very simple example is the binary search. So in the picture above, so in the upper picture, here this is a traditional binary search where we want to find some element 7 on this sorted array, and as you can see, you can take the middle and the middle of the middle, the middle of the middle of the middle, and so on to find this 7. And you take a look order log n time. But then what about if I provide you a prediction? I guess that so I give you an index h, which which is supposed to be close to the I star, which is this 7, the index that I want to find. Let's say this is supposed to be close. And what about let's start from this h and do some algorithm that depends on the gap between this h minus I star, which is the error, right? So here there's actually a simple example, simple algorithm to do that. So you can start from this h, which is 22, and then do 1 step, 2 step, and 4 step, and so on. Do this exponentially increasing step size until you reach some point that is just go past what you want to find. I start 7 here, and then you do a traditional binary search inside of the interval that you find, and this gives you log of h minus I star. So this is a sort of simple example that illustrates so it is possible to utilize the prediction when the prediction is very small, when the prediction is very accurate, the performance is nearly optimal, order 1. When the prediction is very bad, as you can see here, h minus I star can only be at most order n. So in the worst case, it can still be order log n, which is robust. So so motivated by this, we consider a very fundamental problem, which is facility location, and we think about it in the LV framework. So we start with introducing this facility location problem. So facility location problem is a fundamental problem in both operations, research, and computer science. We consider the matrix space version, where the input is a matrix space, where V is a data set, V is a point set, and D is a distance function. And we have X, which is N demand points. We call them demand points. And in the classical setting where it is modeled as an optimization problem, we want to find a set of open facilities, F. This F is simply a subset of points. And when you open some facility at a location, some little f, then you need to pay a cost of W of f. And the objective function here is to minimize the opening cost, basically the sum of WFs that you have open, and plus the connection cost from every data point to some facility. So this f sub I is some facility that you can choose from f to be assigned to. And here, like clearly you want to find the nearest one from this xi. So that's the classical setting. And in our talk, we consider the online setting. So the input is still the same, just that how they are presented and how the algorithm make decision are different. So so in the online setting, when the ith point xi arrives, the algorithm must irrevocably assign xi to an open facility. So what do I mean by irrevocably? This means if you decide to assign xi to some facility fi, then this decision is final. You cannot change it later on. And furthermore, this online setting requires that you can see the next point xi plus 1 only after you have already done the assignment of xi. So that's the online setting. As in many online algorithm study, we consider the competitive ratio, which is the worst case, really the worst case relative performance of an algorithm relative to the optimal solution of where you have the full information. So the challenge here of the online algorithm is really that you have to make the decision for the ith demand point before you see the subsequent points. So you only have some partial information, and that's why you have a gap between the algorithm and the optimal. So so since we think about the prediction and consider it in the LV framework, so we need to talk about what do we mean by a predictor. So the prediction model here is very simple. So we simply consider a predictor that returns a facility, so supposedly optimal facility for every demand point. So as in this picture, so every time we will receive a demand point, and then apart from that, there will be an optimal solution. Means that in the optimal solution, what facility this demand point should be assigned to. So there's something here in the optimal solution that the algorithm do not know, but the algorithm do know a prediction, which is in this red triangle. And then the algorithm should decide where to assign this point and possibly open this facility. And here we also measure the error by the maximum distance from every prediction to the corresponding optimum. So that's our main parameter, main error parameter eta star and eta infinity, and this is not known to the algorithm in advance. So that's the prediction model. Okay, so then we can talk about our result. So basically, we show that with access to such predictor, online facility, we design an online facility location algorithm that is order mean of log n and log n eta infinity over opt competitive. So let me explain. So first of all, this mean of two terms. The first term is really the robustness guarantee. So when eta tends to infinity, then the second term is very large. So we need to take the first term. The first term is order log n competitive, and this is actually matches previous upper bound by Marathon. And we will go back to this work later. When this eta infinity, which is the error measure, is very small, then we really achieve nearly optimal performance. Here I didn't write, but it's really the case that when eta infinity is 0, this competitive ratio is order 1. This cannot be directly seen from what I wrote because then the log of that thing is negative, doesn't make sense, but for simplicity, I just omit this. Okay, so our algorithm is order 1 consistent and order log n robust. But you might want to ask, so why do I consider the particular error measure of eta infinity? So which is sort of the max or the L infinity norm of this distance from a prediction to an optimal. What about, let's think about the L1 measure, right? So we do show a lower bound that this L1 measure does not help or doesn't make sense. In particular, we show that for some constant eta infinity between 0 and 1, there's a lower bound of basically matches our upper bound log n eta infinity divided by opt competitive, even when this eta y is order 1. So look at this, n eta over opt, this is basically log n over opt, which is very large. And when eta y is order 1, it cannot avoid this n factor. So basically this lower bound shows that this n eta infinity makes sense, and also our upper bound is nearly tight. So that's our main results, theoretical results. Okay, so and this lower bound also generalizes a worst case lower bound of omega 2 log n by Fatakis. Yeah, so we also do experiments to validate our our new algorithm. So we consider several so apart from our algorithm, we consider two very natural baselines. One is simply always follow the predictor, right? So another is don't use any prediction. That's another extreme where is worst case competitive algorithm, which I just mentioned, the Marathon's algorithm, order log n competitive. And here we do two sets of experiments. The first set is really to see how our bound, so how the empirical competitive ratio responds to the eta infinity, the unknown error parameter eta infinity. So to this end, we only use a simulated predictor, which means that we first solve for a near optimal solution for the entire data set, and then we on purpose or deliberately move the optimal solution a little bit by this eta infinity like amount. So then we plot this error versus competitive ratio line. As you can see that our algorithm is strictly between the worst case and the follow predict, which is the performance of the predictor. And as you can see, at some point when the error is large enough, so simply following the predictor is not beneficial. And then, as you can see, our algorithm then stops to be even worse and sticks with this worst case algorithm. So this is really the correct behavior. By the way, this is a real data set from Twitter. So another set of experiments is somewhat more interesting. We think about a greedy predictor. What is a greedy predictor? So it's not a predictor trained using deep learning and so on. It's a very naive one, and we just show that even this naive one can already give us something useful. So what we do here is to use 30% of the data set as a training set, and we simply compute the optimal solution of the facility location. Just use some offline algorithm to compute the optimal. And then when the online demand arrives, which means that's the 70% of test data, we can generate the prediction from the current optimal solution. And then what we do is that we update this optimal solution by adding this new request to the data set the optimal solution should consider and rerun this offline optimization. So eventually we obtain that. So first of all, we observe that this prediction is slightly better than Merson's. Merson is the worst case competitive algorithm. But what is surprising is that our algorithm, which is sort of interpolate between this Merson and follow predict, actually performs very well. It outperforms both. If we use this greedy predictor, we expect that if you plug in an even stronger predictor by using deep learning or reinforcement learning techniques, then our algorithm can perform even better. So that's our results. Next, let's talk about how do we design these algorithms. So the strategy of designing algorithms under this LV framework is actually very sort of conceptually straightforward. So think about it. We have two extremes, which is eta equals 0 and eta equals sort of infinity. So they correspond to two like algorithms. One is just follow the predictor, another is worst case. So which extreme do you want to start? Of course, we want to start with the worst case algorithm, and then we extend it to use a prediction, because that's sort of the more important or difficult part, because we want to guarantee the robustness. And here, the worst case algorithm that we start is the Merson's algorithm we just mentioned. So to this end, we have to talk about what's happening inside of the Merson's algorithm, and then we can talk about what do we do to modify this to make it perform better when the prediction is good. So for simplicity, let's first consider a uniform opening cost case where you just pay some unit cost when you open every facility. So and this algorithm first maintain an empty facility set, so you don't open anything at the beginning. And the algorithm is very simple. It consists of 3 steps. So whenever some point xi arrives, so what do? I first compute what's the current distance from this xi to the current open facilities, and I use this delta distance as a sort of threshold, and I look at delta over W. W is the opening cost. So I look at how expensive this current solution. So basically, I try to assign this xi to the nearest point in F. And if this is too costly, even more costly than opening a new facility, then I will open the facility at xi. But sometimes this ratio is not greater than 1. It could be somewhere between 0 and 1. So we open the facility stochastically. So that's the idea. And we, of course, need to update our facility set. And regardless what we do, we always assign this xi to the current nearest facility F. So the behavior of this algorithm is actually quite simple. First, as you can see, from this procedure, we can see that the expected cost of xi basically is at most 2D xif. Why is this? Because the first term is when you open the facility at xi. So the probability is delta over W. The second term is when you don't open the facility and you assign to the nearest of it, which you suffer this delta. So it's 2D xif. So why is this important? Because this relates to the current sort of solution, right? So we can look at the overall performance of this algorithm in this picture. So for the sake of analysis, we think about there's some optimal solution, F star here. So the optimal can open many facilities, but let's now assume there's only one facility that we care about. And then we do a decomposition of the whole space. So we first draw a very small ball of radius opt divided by n. And for the outer rings, we do 2 to the I radius ring. So basically we do 2, 4, 8, and so on. This kind of consecutive rings to decompose the metric space. And what's the behavior here is that when some demand point, okay, so suppose now we already open some facility at some ring, like this red ring. I also call it F ring. Then when some demand point X arrives on or outside this F ring, then we can see that the distance from X to the F ring is at most order 1 times opt, because this point itself is far away already from opt. So paying this cost to F is not too costly. So what happens then if I have some demand point inside of the F ring, which I don't have any facility built? Then in this case, we can see that this random process eventually allows us to show on average, you only pay order 1 times opt cost to build to open a facility at an inner ring. And since you have so now you have, suppose you have M rings, then the competitive ratio would be M order M, right? Because in every ring you suffer order 1 times opt to open a facility, and once you open this facility, every demand point on or outside this ring, it can only contribute to order 1 to the opt. So eventually we can construe that the ratio is order number of rings. And this is helpful, very helpful for the prediction setting. So because we will have this key property where, so suppose now we don't have the empty initial facility. Let's say we already open some facilities F such that every facility is, so every facility opened in opt has some facility opened within distance eta. So this is sort of like we already have a facility that satisfies our error bound. Then Meyerson's algorithm is log n eta over opt competitive. This is what we want, right? So why is this? Because as we show from last slide, the competitive ratio is order number of rings. And how many rings are there? Recall that we do exponentially growing decomposition of the space, and the inner ring is opt over n radius, and the outer ring is eta, which we assume. So log of them is basically what we want. So that's the key property. And how do we use the key property? Is very simple. So our full algorithm is the follows. So when every xi like arrives, we first run Meyerson's as is, don't modify it. But then we add additional step. So whenever we observe Meyerson's algorithm decided to open a facility at some point, we also open the facility at the predicted point. So basically we follow the Meyerson's and open some additional facility at the prediction. Why this works? So this is actually very straightforward. So let's say we have this CI star. Okay, so here's some typo. This should be FI opt as in the second line. So basically this is the optimal facility that XI is assigned to. So by the prediction guarantee, we know that this prediction FI prep is at most eta infinity distance to the optimal solution, FI opt. So we can see that when we open this FI opt, we already have some facility that is within eta infinity distance to the optimal solution. So eventually, the very first facility we have ever opened using this algorithm satisfies that the distance from F to opt is small enough. And this actually satisfies the premises of this key property. and it immediately implies the ratio. So then, yeah. So another small thing I'd like to notice is that in the worst case, our algorithm, so let's say the prediction is very bad, but in the worst case, we observe that what we open is always order one, basically one more times more costly than Meyerson's, because we open the prediction only when Meyerson's did. So our algorithm cannot be 2 times more worse than Meyerson's. So I don't have much time left, so I'll skip the non-uniform case. So then let me conclude. Yeah. So okay. So what I talk about is only one particular recent work about LV framework, and there's actually a lot of recent results on the topic, and people have already think about how to utilize prediction under LV framework to improve the comparative ratio for online algorithms, the space and time for data structures, and running time for many data analysis problems. And I believe there are many more to be done. So that's all for my talk. Thanks.
Okay, thanks for the any questions? Professor Chen, you can just ask your question, I think.
Hi, Shaofeng. Quick question. First, just to confirm, the eta 1, eta infinity, like we don't need to know it in the algorithm, right?
Right. This is very important. As in here, algorithm does not know eta in advance. Yes.
Okay. So a general question is, for this approach of basically like a learning-based or data-driven algorithm design, is it like for each optimization task, we need to think about different predictors, and different predictors will lead to different algorithm design? Is it like an ad hoc or more like a systematic approach?
I think this is a very nice question. So currently what I see is that it's mostly ad hoc. There are attempts to, for a certain family or set of problems, to set some unified approach to design predictors and modeling it and so on. But for most of the problems, of course, it's still sort of ad hoc. And even for the same problem, there are many possibilities to define what is a good predictor for the application. Yeah. Right.
Okay. Thank you.
Yeah. Thanks for the nice questions.
Yeah, I also have a question. Maybe have some relationship between with the Professor Chen's question. So in your models, the prediction is actually the position of the optimal facilities. So if we know if the prediction is not like that, it's the position of each xi. So this is in some sense the full information. This kind of prediction helps?
Okay, so I suppose you are talking about what if the prediction predict the future data set, right? So this kind of predictor has already been considered in another related problem, online caching. So it's like LRU algorithm. So in that work, they consider what's the arrival time of the same page in this caching, in this cache. That's what exactly you ask. Okay, so I suppose it makes sense, but honestly, I don't know. So I mean, for our online facility location problem, I don't know. As I said, there are many sort of prediction models, and for each of them, you need to design a different, very much different algorithm to utilize a predictor. So it's really ad hoc. But I suppose it makes sense. Yeah.
Okay, thank you.
Thanks.